Hello, everybody. Thank you for coming to my talk. My name is David. I'm an employee at Heroku, and I'm going to be talking to you about a technique that I call real-time RESTful. So we've got 90 minutes together, which is quite a while. It's a small enough room. I feel like if anybody has a question, does my audio need to go louder? Is it good? Okay, that's good. Just go ahead and raise your hand. The lights are in my eyes. If I can't see you, wave it around. Yeah, don't hold your questions for the end. Let's make this a little more interactive, so hopefully we're not all asleep by the end of the talk. So yeah, let's get into it. But before we dig in, I'd like to talk about the kind of background to provide some context around what the problem is that we were trying to solve on my team at Heroku that actually led to this talk. So I worked on a product called Heroku Connect, which is an add-on in our add-ons marketplace, whose job is essentially to do a two-way data sync between Salesforce organizations and Heroku Postgres. So we have our client written as an API consumer for the web user interface, which is effectively just a dashboard to allow people to configure mappings between objects in the systems, between Salesforce and Postgres, and to see their data moving. So, when a piece of data shows up on Salesforce, they can see some sort of log entry and some metric of it moving to Postgres and vice versa. So there's a lot happening in the back end asynchronously, actions that are not being instigated by the user that are causing state changes that the user cares to see reflected in the interface. And in the back end, it's basically a gigantic state machine. So we're always transitioning states and polling or reacting to streaming from the different services. A lot's going on, and for our customers to really trust our product, they have to have enough sense of visibility and transparency into the process that they trust that their data is actually getting from one place to another. So when we originally wrote our application, we had our REST API and we were polling via AJAX, based on just like set interval polling. And this just was not cutting it for our customers. We were constantly hearing back from them that they couldn't tell what was happening. The state in the UI wasn't being reflected quick enough for them to feel comfortable that our product was actually working. On top of that, polling, as you guys all know, is extremely inefficient usage of API. So, 90+% of the time when somebody was looking at their dashboard web view and we were polling and actually consuming API calls, they were no ops, right? Nothing was happening, and we were just wasting those resources. And of course, that leads to its own scaling problems because the more people who are concurrently using our application, the more API utilization we have, and it just wasn't going to scale. So again, we have a REST API. We knew we needed to add a real-time channel to it because people needed this responsiveness in their application UI, but we didn't want to dramatically increase the complexity of our application on the client. The client was already complex enough, being an API consumer, having its own components and complex interface. We didn't want to make this client application completely unmaintainable. So now that you have some understanding of the problem that we're tackling, let me step back just a bit and talk about the broader web and where the web has been going. Today's web is service-oriented. So you guys can probably all recall the days when you could describe your entire web stack with an acronym, right? I'm running a LAMP stack. Everybody knew what that meant. Linux, Apache, MySQL, PHP. Put a load balancer in front, maybe stick memcache off to the side, and you've pretty much got your infrastructure. Really easy. You're using one relational data store. Your request response cycle encapsulates all of your business logic, and the server is entirely responsible for rendering all the content that comes down to the client. This is a bit outdated. Today's web applications look more, That's not quite right. Yeah, they look like this. Much more service-oriented architecture where you have multiple services, either public, available to the wider internet, or private services that communicate to other services only. Services being comprised of one or more processes, mostly talking HTTP to each other, and in the case where they need more of a broadcast, one-to-many communication, pub/sub is the common method to use. But most importantly, in all of this, is that little orange box at the top. So now that our applications are more commonly just networks of services talking to each other, the client in our web browser becomes just another service, consuming the public services published by our server. This didn't happen overnight. First we had services that would publish an API, and they called it, platform play, right? So then we had other clients, other than additional services, consuming those same APIs. This kind of coincided with the rise of native mobile applications. And so we began to see the expansion of the platform past third-party integrations to our own native mobile clients. And finally, JavaScript tools matured to the point where it became feasible to begin to treat our web browser as yet another type of client. We developed JavaScript templating, client-side MVC, web components, all technologies that help us manage actual client interfaces in our web browser in JavaScript. So long story short, we've had plenty of time to understand how HTTP APIs are actually created and develop best practices around the way the machines talk to one another. Heroku published a document a little while ago that you may have seen that's an HTTP API design guide. I recommend you read it if you hadn't yet. This is just a snippet from the table of contents, but it's very opinionated. It contains a lot of material on how to, we believe, properly design HTTP APIs. But really the point here is that there's been a lot of thought and a lot of consensus around the way that you build these APIs. And as a result, what used to be novel is now table stakes, right? When you think of your web application as a network of services, the platform is no longer an add-on, it's a core part of your architecture. And so you have to be able to think about your architecture as emanating from your platform outward. So the web is increasingly real-time. We're now creating web applications that actually look and act like apps, and as a result, our users have developed an expectation of responsiveness. They don't care that your application is running in a web browser instead of on their mobile device. They care that it's usable and it's fast. They care that the state is consistent between the client and the server. They may not be able to express to you in those terms, those desires, but that's how they want it to work. We all know the common fallacies of distributed computing, but those don't really mean anything to a user. Like you tell a user, network latency is non-zero, networks are unreliable. They don't care, they just know that their photo didn't upload or something like that. The good news is that it's not as hard as it used to be to make this work. I remember back in the early days of pushing to web clients, we used this abomination of AJAX, I think we called Comet. It's basically long polling, where the client would issue a request to the server. The server would hold that request open until it had some data to send down to the client. And then once that server had something to say, it would respond, and the client would immediately turn around after receiving that data and issue another AJAX request to the server, and the process would start all over. Then we even misused the web even more by using flash sockets to open socket connections between client and server. Luckily, those days are long behind us, and we now have WebSockets, which they're not the easiest thing in the world, but the compatibility is improving, as you can see from this chart, and there are enough tools out there now that they're not too difficult to use anymore. But just because something is now easier to do doesn't mean that it's easy to do it right. So a little thought experiment. Think of a web product that you've built, preferably one that interfaced with a REST client on the server. Now think about the design of a real-time streaming transport that you might add to that product. Many of you are smarter than me, but if you're like me, then you immediately begin to think about actions in terms of events and event types and types of things that could happen in the system that the client might want to know about and react to. And so then you think about those types being correlated to payloads of data in certain known formats. And then you begin to think about the process of, okay, how will my client react to a given event type with an event payload? And what are the different parts of my user interface that might need to react to any given event type? And so you start iterating your mind through the different UI components that need to update themselves based on an event. And if you're like me, then your head begins to hurt thinking about the complexity of implementing all of this. All this is to say that even though the web is increasingly real-time, real-time transport design is far from a solved problem. I think of a technology as being mature when patterns are well established, well understood, well socialized, when I can jump into a code base that I'm unfamiliar with, and I can begin to quickly understand how they've implemented something because it follows a common pattern that I'm used to or uses a technology that's well established. I kind of feel like real-time on the web is just not there yet. There are too many bespoke solutions. There are too many one-offs. There's too much documentation that you need to write to explain your process that begins to get out of control as it grows and grows. So all that to say, the web is complicated. We tend to think about platform and real-time as kind of like one versus the other, but in reality, we really need to be doing both. It's not really a choice. Like, we don't have a choice not to do platform anymore because it's an expectation of third-party services and even of your own clients, like mobile clients, that you're going to need a RESTful API. And then in order to have your web client act like an actual application, you need this real-time component also. The problem is that these two things are commonly solved orthogonally, which means that they easily go out of sync. When you're adding something to your REST API, you have to think about, okay, is there a new event type that my real-time transport needs to add in order to react to this change in my API? They have human resource contention. So when I'm solving these problems separately from each other, then I have to choose teams of people who are going to go work on these problems, and I may not have enough people to do both. So I may have to prioritize one over another. That's actually where Heroku Connect was in our kind of startup-y phase, where we didn't have time to do both, and so we chose polling to the detriment of our product experience. There's at least twice the surface area for errors to appear. And we all know that errors on the client are notoriously difficult to debug because you don't have control over the entire application state. Part of it's running in a browser on somebody else's machine, and you can't reproduce it, and you're tearing your hair out. We also know that event-related bugs or callback-related bugs are notoriously difficult to track down as well because you don't have a coherent stack with which to kind of trace through your problem. Your problem may be distributed between stack frames that are actually in separate processes or separate parts of your application. And so when you combine both of those things together, you really have a hard time solving problems. So let's look at a common architecture that people use, or that I've seen used at least, to solve this real-time transport issue. Of course, you have to have some sort of daemon that is the server providing the connection, the stream connection down to the client, usually via WebSockets. You have some sort of business logic in your application that is triggering an event to fire. That event includes, like I said, some sort of data payload and some event type. Commonly also, when you think about reacting to changes in a user interface, you want to know what users are being affected. So it's a common pattern to attach an event type and payload to a user or to a set of users. And then because we don't want to necessarily couple our business logic to our stream server, we use pub/sub to be able to disintermediate the publishing of that payload back down to the client. The channel we use for pub/sub is commonly the user ID or the set of user IDs, so that that can map kind of one-to-one to our client. So on the client side, we have something like raw WebSockets or Socket.io consuming this stream and listening for messages that are routed from pub/sub down through the stream server. And once a message was received, then that receiver turns right around and emits that event back out to the client system. And multiple UI components, one or many, are listening for those events and reacting to them by mutating state, mutating presentation logic, performing all these operations in order to try to converge the user interface of the application to the reality of the current state. So yeah, that's a common approach I see taken. So we've kind of like outlined a bit of the mess that we're in here, trying to solve platform in real time in regard to our web app architecture. But before we get into solutions to the problem, I'd like to kind of spend a little bit of time reframing. So when we think about events, what we're actually thinking about is a proxy for a set of state changes or data mutations. So X happened is actually just shorthand for objects A, B, and C have been mutated. If instead of events, we could simply enumerate each and every one of those state mutations, including the second, third, and nth degree mutations, like changing aggregates. Say, like you have a count of messages in your inbox, right? That's also a separate, distinct mutation from the individual message appearing in the inbox. Then, if we could enumerate all of those changes, the event itself would be useless. And the reason that we tend to think in terms of events, or at least I do, is because our brains are causally driven, and events to us form a natural cause and effect relationship. But computers don't really have any inherent notion of causality. They care about data flow through systems. And so our causally driven minds are then creating this implicit contract based on our ability to derive cause and effect relationships in our code. And those relationships, they spread their tendrils out through the entire presentation layer. And that's why those types of clients are so difficult to understand, to maintain and untangle, is because we've taken this one concept, this one idea, and we've kind of in our heads implicitly distributed it out through the entire code base. If we agree that state change is what we're after and not necessarily event propagation, then all we really need to know about is all the operations which change state. And so our goal then is to isolate those mutations. And once we've isolated them, then we have all the hooks we need to enumerate them explicitly. So then our streaming contract can become both comprehensible and maintainable because we've taken the work that was previously implicit from event type to data mutation. We've isolated it into one place in our code. We've explicitly enumerated those state mutations, and then we can take that and propagate them through our real-time transport. And the result is that we get rid of all of this spooky action at a distance that happens with an event-based system where the name of an event type means any number of side effects to our client interface. And the number and the range of effect is essentially unknown to us unless we know the entire code. Another point I'd like to make is that our existing REST API can fully describe our application state. If this wasn't true, then we wouldn't be able to make clients which were fully featured and both consumers of the API itself. So the fact that the API is already existing and that we already have a consumer for it makes it a perfect choice for our real-time transport contract as well. So you can probably guess at what all of this is leading to. There's a better way to solve our problem of adding a real-time transport without making our client app entirely too complex. So let's review a bit. This is the same architecture slide for real-time transport I had before. So remember, pub sub channel per user. User authenticates to the stream producer with some sort of private key, session identifier out of a cookie or an access token or something like that, which is passed to the identity service, whether that be coupled to the business logic or whatever, for verification. Basically, we need to know, like, who is this user, right? When the user tries to connect to a WebSocket. There are ways to do that. Stream producer subscribes to the user-specific pub sub channel via Redis or whatever pub sub we're using. Events are published to that channel and flow down to the client, and then the client logic has to deal with each and every event type. Alternatively, this slide looks very similar in the number of kind of like blocks here, but there are some very important distinct differences. Mainly, we've kind of turned this 90 degrees where instead of making this user-centric, our pub sub channel is per REST endpoint. The client asks the stream producer to subscribe to REST endpoints on its behalf because the client knows which endpoints it cares about. And then on any state change event, the REST API determines all relevant endpoints that are needed to be refreshed by that data mutation and publishes to channels on those endpoints, the pub sub, which stream down from the stream server back to the client. So then the client deals with those data payloads the exact same way that it would if it had made an AJAX request to the same endpoint and received a payload back. So no solution is a cure-all, and no analogy is perfect. And we are definitely making an analogy when we use REST to describe a real-time transport. So there are some sharp edges and some challenges to overcome. So let's talk about what challenges we faced at Heroku Connect solving this problem. Obviously, it's necessary to isolate the data mutations. This was fairly easy to do for us. Luckily, our architecture is one single data store. It's a Postgres database. So that's our one source of truth, and we only have one REST API that's actually changing state on that data store. So our backend API is written using Django REST framework. Django has an ORM, which provides hooks, as most ORMs do, into post-save and post-delete. So after basically any write operation, we have a hook that we can call, and that's basically all we need for state isolation, right? If your architecture is more complex than that, if you have multiple APIs writing to the data stores or multiple data stores being written to, then you probably want to encapsulate that into a data service if you haven't already, and have that service be the single point of entry for all writes to all of your data stores. Have that fan back out from that single point to all of your data stores. And then that single point of entry would be your point of isolation for data mutation. So another challenge we faced was authentication. Since our pub sub channel is no longer user-based, we not only have to have a way of identifying which user it is that's connecting to our stream producer, but we also have to know if they're allowed to subscribe to that individual REST endpoint. Luckily, RESTful APIs have already solved this problem for us, and so we don't need to solve it over again. All we have to do is when a subscription request comes into the stream producer, it then makes a head request to the REST API using the same authentication mechanism as you would a normal API call, whether that be access token or a session cookie in a cookie bag or whatever. And if that call, if the head request comes back as a 200, then you know that that user has access to that resource. And you can safely subscribe to it. And then from that point on, know without a doubt that anything that comes through that channel is allowed to be sent back down to the user. The hardest challenge that we faced was determining which API endpoints have changed due to some change in state. And this requires the active participation of our REST API. Because the REST API, after all, is the authoritative source of what endpoints are, what they mean, right? So we created a registry of our model types to all of the endpoints that could potentially be affected by that model type. And so then in our post, save, and delete hooks, we can then iterate through each one of those endpoints in the registry, render out a fully qualified path based on the model instance. For instance, it's pretty common to pull out a primary key to render a detail endpoint path, right? Just like /object name /ID. And so after all of those endpoints are rendered, we just loop through them and actually render the response payload from the API and pipe that all through pub/sub, because now we have the channel name and we have the JSON or XML or whatever payload. And so that solves the what endpoints have changed problem. A lot of you out there are probably thinking at this point, this sounds really slow and really performance intensive. And that can definitely be true depending on the write load of your application. If your application is read heavy, then maybe you don't want a streaming API to begin with. But for write heavy applications, this can become really expensive really fast. Luckily, Redis pub/sub, and I would be surprised if others didn't follow suit, has a way to ask if there are any subscribers for a given channel. And so we have a fast path to avoid rendering API payloads if there are no subscribers for a given endpoint. So if nobody's listening, right? And the rendering of the endpoint itself, of the fully qualified path, is pretty cheap. It's basically, it amounts to string substitution. So that's not a concern. It's actually running through the API and making the API call for each and every endpoint, for each and every model that could have been affected. That's the expensive part. So we are currently doing that synchronously in our web server request response cycles, in our queue workers for asynchronous tasks. And we're seeing good enough performance to get by for our application. If your application is higher scale than ours, then you might consider moving all of those payload renderings off onto their own worker queue with their own queue consumers and worker pool. The obvious impact of that will be increased latency in getting this data through back to the client. But latency versus load is always a balancing act. So that's pretty much the gist of the theoretical point. We're gonna dive into some code in a minute, but I wanted to pause first and see if anybody had any questions before we did that. Yeah.
How do you manage authentication with WebSocket? Because you're only providing the user when someone who's not authenticated with a new username could send a request and it's cookieless, the way you described.
Not necessarily cookieless. Not necessarily. So you have a few options. You can use a third-party cookie to ship an access token down to the client that you access from your REST API when you initially render the page. I'm sorry, I should repeat the question. Question was, how do you authenticate a user and keep a user from misrepresenting who they are when you can't trust the client? So it comes down to access token or some sort of other session or private ID, right? You have to have a way to get that, right? So either from a third-party cookie that round trips and then bounces back to your process, that you inject the access token from that bounce into the page payload before you send it down, which is how the Heroku bouncer works for Heroku applications. They do their OAuth dance, they come back to us, and the access token for a Heroku user is actually in the headers of the request that comes back to our web server. And so we inject that access token into the page, send it down to the client, and that client sends the access token back through the WebSocket to us. And we store the access token on the socket so that when we make API calls to the REST API from that stream producer, we have the access token there that we can stuff in an auth header. The other way to do it is have the active participation of the client sending the session cookie information to the WebSocket when it connects. So that would require cookie storage, and yeah, it would also require that you have like a login process on the actual application that is the same as your client, right? As opposed to like a third-party authentication mechanism. Does that answer your question?
Yeah,
Right.
absolutely.
Cool.
Some of the challenges that I've seen with cookie layer, some shops prohibit JavaScript readable cookies, for example. Then you're going to have to do a token.
Yeah, so if you can't use cookies, then you can't have any sort of state on the web, right? Which, you know, some people argue that's the purest view. But in that case, like if you have to absolutely avoid doing that, then every time the user opens a browser window and navigates to your site, you know, they're going to be presented with some sort of login form to provide authentication credentials that would then get sent through the WebSocket, and you know, you would use HTTP basic auth or something like that to authenticate back to the REST API to identify what user they are. Anybody else have a question about anything that I've covered so far before I move on? Yeah. I don't see why it couldn't be, but I've primarily thought about it in terms of WebSockets instead of just like regular TCP sockets. So if you...
Sorry, I meant like as an addition to your REST API.
Yeah, I know what you mean. So like the Twitter streaming API as an example, like that's intended for server to server primarily and not as like a client interface necessarily. There's no reason you couldn't do that. We haven't implemented that for our product. We've focused mainly on the stream producer making WebSocket connections to web clients. But a socket is a socket, right? So like once you send it over the socket, then who cares who's on the other end, right? Okay, if nobody else has any questions, then I will redo my screens here and dive into some code.